The problem was the wires, not the transistors, not the resistors, not the capacitors. The wires that connected them, the hair-thin copper conductors that a skilled technician had to solder between each component, one connection at a time, in a process that was slow, expensive, error-prone, and fundamentally incompatible with the direction electronic technology needed to go. In the last episode, we watched the transistor solve one problem and leave another one standing. Vacuum tubes were gone, or at least going. The heat, the fragility, the slow warm-up, all of that had been solved by a sliver of germanium, and two gold contacts pressed impossibly close together at Bell Labs in December 1947. But a transistor was still, physically, one object. A circuit with 100 transistors needed 100 transistors wired together, plus whatever resistors and capacitors the circuit required, plus the wires connecting all of them. The size of a circuit was the size of its components plus the size of their interconnections. The reliability of a circuit was limited by the reliability of its weakest solder joint. Nobody had solved that yet. In 1958, nobody quite knew how. America in 1958 was in the middle of a technological crisis that the Soviet Union had created. Sputnik had launched on October 4, 1957, and the psychological impact of the Soviet Union placing a satellite in orbit before the United States had done so was not primarily about the satellite itself. It was about what the satellite implied, that the Soviet Union had developed rocket technology capable of placing a payload in orbit, which meant rocket technology capable of delivering a warhead to any point on Earth. The American military's response was a comprehensive reassessment of its technological programs. The electronics problem was high on the list. Guidance computers for ballistic missiles, electronic systems for the aircraft that would deliver or intercept weapons, communication systems that would coordinate a response in a crisis. All of it was limited by the size, weight, and reliability of discrete component electronics, built the way electronics had always been built, one soldered wire at a time. DARPA, established in February 1958 as a direct response to Sputnik, began funding research on the miniaturization problem from every angle its program managers could think of. The military service branches ran their own parallel programs, and the electronics companies that supplied military equipment were working on the problem independently, with and without contracts, because whoever solved it first was going to own the next decade of the industry. Texas Instruments was one of those companies, founded in 1951 by Patrick Haggerty, Cecil Green, and Eric Johnson, as a spin-off of an oil exploration instrumentation business. Texas Instruments had already made its mark on the transistor era by 1958. The company had produced the first commercial silicon transistor in 1954 and had partnered on the Regency TR-1, the world's first commercially available transistor radio, the same year. We covered that radio at the end of the last episode. It was Texas Instruments' first proof that a transistor could leave the laboratory and end up in someone's shirt pocket. By 1958, the company was pursuing the research that would let it compete with the electronics giants, General Electric, Westinghouse, RCA, that had built their positions in the vacuum tube era and were now scrambling to catch up in the transistor one. Jack Kilby arrived at Texas Instruments on May 1, 1958. Jack St. Clair Kilby was 34 years old when he arrived in Dallas. A native of Great Bend, Kansas who had spent the previous decade working for Centralab, a manufacturer of electronic components in Milwaukee. Kilby had studied electrical engineering at the University of Illinois, graduating in 1947. The same year Bardeen and Brattain built their first transistor at Bell Labs, though Kilby had no connection to that work at the time. He spent his decade at Centralab on miniaturization problems, specifically on the ceramic wafer assemblies the company was developing for hearing aid electronics. The hearing aid was the consumer application that most aggressively demanded miniaturization in the early transistor era. A person wearing a hearing aid needed the electronics small enough to fit behind an ear, which pushed the limits of what discrete component assembly could achieve even after the transistor had already shrunk the components themselves. Kilby's decade of work on hearing aid miniaturization gave him a specific and practical understanding of the limits of discrete assembly. He knew what could be made smaller through better manufacturing, and what could not be made smaller regardless of how good the manufacturing was. He knew where the fundamental limits sat, and the wiring, not the components, was where those limits lived. He had also been developing a different idea, informed by his Centralab work and by the published semiconductor physics literature. What if all the components of a circuit, not just the transistors, but the resistors and capacitors too, could be made from the same semiconductor material, in the same manufacturing process, on the same piece of semiconductor? If everything was made from the same material in the same process, nothing would need to be connected by wire afterward. The connections could be part of the manufacturing itself, formed in the semiconductor material by the same techniques used to create the transistors and resistors. No wires, no solder joints, no assembly. The entire circuit would be a single piece of material. This was the idea Kilby carried into Texas Instruments in May 1958. He didn't have it fully worked out. He had the concept, the recognition that the wiring problem could be solved not by making wires smaller or more reliable, but by eliminating the need for wires entirely. He arrived during the 2 weeks in July when most of the company's employees were on vacation. Kilby was new and hadn't yet accumulated the vacation time to take those 2 weeks off. He stayed at the lab. In the empty laboratory, with nobody else around, Jack Kilby worked out the integrated circuit. The notebook entry that documents his thinking is dated July 24, 1958. It's brief, a few sentences and a sketch, but it contains the essential concept. Kilby wrote that it appeared feasible to make all circuit components on a single monolithic crystal of silicon. The components would be formed in the silicon by the same diffusion and deposition processes used to make transistors. The connections between components would be formed on the surface. The result would be a complete circuit in a single piece of semiconductor. That entry describes what we now call the integrated circuit. The concept that would eventually allow billions of transistors to sit on a chip the size of a fingernail is present in Kilby's July 24 notebook entry in its essential form. This wasn't an accident in the sense of being random or unintended. Kilby had been thinking about the problem systematically and had arrived at a specific approach. What was accidental, if the word applies at all, was in the conditions that produced the insight. 2 weeks of colleagues on vacation left Kilby alone in the laboratory, without the daily demands of ongoing projects, without meetings, without anyone else's priorities competing for the equipment. That uninterrupted stretch is what let the concept crystallize, and it's what let him start testing it immediately, without having to negotiate for lab time. The prototype used germanium rather than silicon, the material Kilby knew best from his Centralab years, which let him focus on proving the circuit concept rather than wrestling with an unfamiliar material's quirks. The circuit he built was the simplest possible demonstration, a single oscillator, made of a transistor and the resistors and capacitors needed to make it oscillate, all formed in one piece of germanium. The demonstration was set for September 12, 1958. Texas Instruments management, Haggerty and the other senior executives, gathered in the lab to watch Kilby connect a power supply to the germanium chip and observe the output on an oscilloscope. The oscilloscope showed a sine wave. The circuit was working. Robert Noyce was working on the same problem at Fairchild Semiconductor in California, and his solution arrived roughly 6 months after Kilby's. If you watched our last episode, Noyce's name might be familiar. He was one of the 8 engineers who walked out of William Shockley's company in 1957 to found Fairchild. The traitorous 8, Shockley called them, and never really let it go. The simultaneous, independent invention of the integrated circuit by 2 people who had no knowledge of each other's work is one of the most discussed cases of parallel discovery in the history of technology. Noyce was 30 years old in 1958, a physicist from Grinnell, Iowa, and he was approaching the miniaturization problem from a different angle than Kilby. Where Kilby had focused on making all components from the same semiconductor material, Noyce was focused on a specific manufacturing technique. The planar process that his colleague Gene Hoerney had developed at Fairchild, which allowed all of a transistor's features to be formed on the flat surface of a silicon wafer rather than at different depths within the material. The planar process had a specific implication that Noyce recognized. If all of a transistor's features sat on the flat surface, the connections between transistors in a circuit could also be formed on that surface, using metal deposited on top of an insulating layer of silicon oxide. Those connections wouldn't be wires soldered between components. They'd be part of the manufacturing process itself, formed on the wafer with the same precision as the transistors. Noyce wrote his notebook entry describing the interconnected planar circuit in January 1959. His design had specific advantages over Kilby's first attempt: silicon instead of germanium for better high-temperature performance, and a planar interconnection technique that was far more compatible with manufacturing at scale than the wire bonding Kilby's first prototypes had relied on. The patent dispute that followed, Texas Instruments filing on Kilby's concept, Fairchild filing on Noyce's implementation, occupied lawyers for a decade before it resolved in a cross-licensing agreement letting both companies use both sets of patents. The resolution acknowledged that both men had made essential, independent contributions. That resolution holds up. Kilby invented the concept. Noyce invented the manufacturing approach that made the concept commercially viable. Neither invention was complete without the other. The first commercial application of the integrated circuit was not the military system that all this miniaturization funding had been chasing. Texas Instruments had been working on military applications from the start. The Minuteman missile guidance computer was an early integrated circuit customer, and the military's willingness to pay premium prices for the performance advantage was an important part of what funded early manufacturing development. But the specific application that brought integrated circuits to the mass market was the hearing aid. That connection wasn't coincidental. Kilby's decade at Centralab had been spent on hearing aid miniaturization. His understanding of discrete assemblies limits had been built in that context. The concept of the integrated circuit had emerged, at least in part, from thinking about the exact constraints of hearing aid design. Texas Instruments' first commercial integrated circuits went to hearing aid manufacturers in the early 1960s, letting hearing aids get smaller and more reliable than anything discrete assembly could achieve. The revenue from that market helped fund continued development of integrated circuit manufacturing. The irony is specific, and it's the kind of irony this channel exists to dig up. The technology that would eventually build the most complex electronic systems ever constructed, the microprocessors in modern computers, the switching systems of the Internet, was first put to work in devices designed to help people hear the world around them. Getting from the integrated circuit to the microprocessor, a single chip that could function as a whole computer, took about a decade from Kilby's 1958 demonstration. Each step was manufacturing progress, processes that could place more transistors on a chip with greater reliability. Smaller transistors meant more of them fit in a given area, which meant more complex circuits could live on a single chip. Gordon Moore, one of Fairchild's co-founders, and later Noyce's co-founder at Intel, observed in 1965 that the number of transistors on an integrated circuit was doubling roughly every year, and projected the trend would continue. That projection became known as Moore's Law, and it held for decades, though the doubling period stretched from 1 year to roughly 2 as the manufacturing challenges got harder. Moore's Law was never a physical law. It was an empirical observation about the pace of engineering progress. The engineers driving that progress weren't constrained by it. They were creating it. through the systematic application of research and capital to the problem of making transistors smaller and more reliable, year after year. Intel, founded by Noyce and Moore in 1968, produced the first commercially available microprocessor, the Intel 4004, in 1971. It placed 2,300 transistors on a single chip, a circuit that would have needed 2,300 individual transistors, plus resistors, capacitors, and the wiring to connect them all, in discrete form. On the 4004, every one of those 2,300 transistors sat on a chip the size of a thumbnail. The 4004 was designed for a Japanese calculator company, Busicom, that needed a computer on a chip for its calculator line. The application wasn't a grand vision of a computer for every person. It was a practical commercial problem, a calculator, that needed a specific technical solution. The accident, if the word applies, was in the generality of the solution. A microprocessor that could be programmed to do calculator math could also be programmed to do anything else computable. The calculator was the occasion for the invention. The invention itself was general, and that generality is the reason a chip built for a calculator company in Japan in 1971 is, in a direct lineage, the ancestor of the device you're probably watching this on. Jack Kilby received the Nobel Prize in Physics in 2000, sharing it with Georges Ulfarov and Herbert Kromer for contributions to semiconductor technology. The Nobel citation credited Kilby's invention of the integrated circuit as the foundational achievement the prize was recognizing, the technology that enabled the information age, that underlies every digital device, that is the basis of the computers and communication systems of the modern world. That description was accurate and understated at the same time. Kilby was 76 years old when he received it. He'd spent the 4 decades since 1958 at Texas Instruments, working on successive generations of semiconductor development, and had already received the National Medal of Science in 1969 and the National Medal of Technology in 1990. But the Nobel, arriving 40 years after the invention it honored, was the acknowledgement the broader scientific world gave to something the electronics industry had already understood the significance of since September 1958. Robert Noyce died in 1990, 10 years before that Nobel was awarded. The Nobel Prize isn't given posthumously, so Noyce's co-equal contribution to the integrated circuit could be described in the citation, but couldn't be recognized by the prize itself. The hearing aids that motivated Kilby's decade at Centralab, and that were among the first commercial applications of the integrated circuit, are still manufactured, though the chips inside modern hearing aids bear no physical resemblance to Kilby's germanium prototype. Today's hearing aid processors carry millions of transistors on chips, a fraction of a millimeter across. The wires that were the problem in 1958 are gone, not just from hearing aids, from every electronic device on Earth. The integrated circuit eliminated the need for wires between components by folding the connections into the manufacturing process itself, and that process has been refined over 6 decades until the connections inside a chip are measured in nanometers rather than millimeters. The chip Kilby demonstrated on September 12, 1958, the germanium oscillator that produced a sine wave on an oscilloscope in a Dallas laboratory, is preserved today at the Smithsonian's National Museum of American History in Washington, D.C. It's small, a sliver of germanium a few millimeters on each side, with gold wire bonds connecting the components. Fragile-looking, the kind of object you'd walk past without a second glance if you didn't know what it was. It is what it is, the first integrated circuit, the device that solved the wiring problem by eliminating the wires, the invention behind every digital device built since, the computers, the smartphones, the servers, the controllers in aircraft and cars and medical equipment, the systems carrying information across the globe. All of it traces back to a 2-week July vacation in Dallas, an empty laboratory, a notebook entry dated July 24, 1958, and a new engineer who'd spent the last decade of his life thinking about hearing aids. The transistor solved the tube. The chip solved the wire. What's left, once you can put a computer on a single piece of silicon, is a different question entirely. Not how do we build the circuit, but what do we build with it? That question is where the next episode picks up.